Climate change is one of the greatest challenges facing humanity in the 21st century. It poses significant risks to our planet, including rising sea levels, more frequent and intense extreme weather events, and shifts in weather patterns. These changes have profound implications for agriculture, the backbone of our food supply. As temperatures rise and rainfall patterns become more unpredictable, farmers around the world face growing uncertainty about their ability to produce the food we need. Understanding the economic impacts of climate change on agriculture is crucial for developing effective adaptation and mitigation strategies. By quantifying the costs and benefits of different responses, economic analysis can inform policy decisions and guide investments in climate-smart agriculture. This essay will explore various economic analysis approaches used to assess the impacts of climate change on agriculture, highlighting their strengths and limitations. From computer models simulating crop growth to analyses of historical data and sophisticated economic models, researchers employ a range of tools to understand this complex issue. Each approach offers unique insights into the challenges and opportunities presented by climate change, providing valuable information for policymakers, farmers, and other stakeholders. In the following sections, we will delve into the specifics of each method, providing clear explanations and real-world examples to illustrate their application. By understanding the strengths and weaknesses of each approach, we can better appreciate the importance of using multiple methods in concert to gain a comprehensive understanding of the economic implications of climate change for agriculture. Crop simulation models are powerful tools that allow scientists to predict how different crops will respond to changes in climate variables such as temperature, rainfall, and carbon dioxide concentrations. These models are essential in understanding the potential impacts of climate change on agriculture and food security. These models use mathematical equations to represent the complex biological processes involved in plant growth, taking into account factors like photosynthesis, respiration, and water uptake. By simulating these processes, scientists can gain insights into how plants interact with their environment and how they might perform under different conditions. By inputting different climate scenarios, researchers can use these models to estimate future crop yields under various climate change projections. This helps in planning for future food production and ensuring that we can meet the demands of a growing population. One of the key strengths of crop models is their ability to isolate the effects of individual climate variables on crop growth. This means that scientists can study the specific impacts of temperature, rainfall, or carbon dioxide levels independently. This allows researchers to identify the most critical climate risks for specific crops and regions. By understanding these risks, they can develop strategies to mitigate negative impacts and enhance crop resilience. For example, a crop model might reveal that maize yields in a particular region are highly sensitive to changes in temperature during the flowering stage, providing valuable information for developing heat-tolerant maize varieties. This can lead to the creation of crops that are better suited to future climate conditions. However, crop models also have limitations. They are complex and data-intensive, requiring detailed information about soil properties, crop management practices, and other factors that can influence crop growth. Gathering this data can be challenging and time-consuming. This data is not always readily available, particularly in developing countries. Limited access to accurate and comprehensive data can hinder the effectiveness of crop models in these regions. Additionally, crop models are simplifications of reality and may not fully capture all the factors that affect crop yields in the real world, such as the emergence of new pests and diseases or the adaptive capacity of farmers. These unforeseen variables can significantly impact crop performance. Despite these limitations, crop models remain valuable tools for assessing the potential impacts of climate change on agriculture. They provide a framework for understanding complex interactions and can guide research and policy decisions. By providing insights into how different crops may respond to future climate conditions, these models can inform decisions about crop selection, planting dates, and other management practices that can enhance resilience to climate change. This proactive approach is crucial for ensuring sustainable food production in the face of a changing climate. While crop simulation models look to the future, empirical yield models focus on the past, using historical data to analyze the relationship between climate variables and crop yields. These models statistically relate observed crop yields to historical weather data, such as temperature, rainfall, and solar radiation, to identify patterns and correlations. By analyzing these historical relationships, researchers can estimate how changes in climate variables have affected crop yields in the past, and use this information to project future impacts. One of the main advantages of empirical yield models is their reliance on real-world data. By analyzing actual crop yields and weather patterns, these models capture the complex interactions between climate and other factors that influence crop growth, such as soil conditions, pest and disease pressure, and management practices. This grounding in real-world observations makes empirical yield models particularly useful for assessing climate change impacts at regional and local scales, where variations in these other factors can be significant. However, empirical yield models also have limitations. Their reliance on historical data means they are limited in their ability to predict the impacts of unprecedented climate conditions that lie outside the range of historical observations. Additionally, these models assume that the relationships between climate and crop yields observed in the past will hold true in the future. However, this assumption may not always be valid, as factors like technological advancements, changes in crop varieties, and adaptations in farming practices can all influence how crops respond to climate change. Despite these limitations, empirical yield models provide valuable insights into the historical impacts of climate change on agriculture. By analyzing past trends, these models can help us understand how different crops and regions have been affected by climate variability and identify areas that are particularly vulnerable to climate change. This information is essential for developing targeted adaptation strategies and prioritizing investments in climate-smart agriculture. Furthermore, empirical yield models can be integrated with modern technology to enhance their predictive power. For instance, combining these models with remote sensing data and machine learning algorithms can provide more accurate and timely insights. This integration can help policymakers and farmers make more informed decisions, ensuring that agricultural practices are resilient and sustainable in the face of changing climate conditions. Ultimately, the goal is to create a more resilient agricultural system that can adapt to both current and future climate challenges, ensuring food security for generations to come. Agro-economic models go beyond simply predicting crop yields, integrating climate data with economic factors to provide a more comprehensive assessment of climate change impacts on agriculture. These models are essential in understanding how various elements interact within the agricultural ecosystem. These models combine biophysical data, such as crop yields and water availability, with economic data, such as prices, costs, and trade flows, to simulate the behavior of agricultural markets and assess the economic consequences of climate change. This integration helps in predicting market trends and preparing for future uncertainties. By linking the biophysical impacts of climate change to economic factors, agroeconomic models can provide insights into a wide range of issues, such as the effects of climate change on farm incomes, food prices, and land use patterns. These insights are crucial for developing strategies to mitigate adverse effects and enhance agricultural sustainability. For example, an agro-economic model might be used to assess the impact of a severe drought on wheat production in a particular region, taking into account not only the decline in wheat yields, but also the resulting increase in wheat prices and the potential for farmers to switch to more drought-tolerant crops. This adaptability is key to maintaining food security in the face of climate variability. The strength of agroeconomic models lies in their ability to capture the complex interdependencies within the agricultural sector and between agriculture and other sectors of the economy. This interconnectedness highlights the broader implications of agricultural changes on the overall economy. By considering both biophysical and economic factors, these models provide a more holistic view of the potential impacts of climate change on agriculture. This comprehensive approach is vital for creating effective policies and strategies. However, this complexity also comes with challenges. Agroeconomic models require large amounts of data and can be computationally demanding to run. The need for advanced technology and expertise can be a barrier for some regions. Additionally, like all models, they are simplifications of reality and may not fully capture all the factors that influence agricultural markets and economic outcomes. This limitation necessitates continuous refinement and validation of the models. Despite these challenges, agroeconomic models are essential tools for understanding the economic implications of climate change for agriculture. By providing insights into the potential impacts on farm incomes, food prices, and other economic variables, these models can inform policy decisions aimed at mitigating the negative consequences of climate change and promoting the resilience of the agricultural sector. This proactive approach is crucial for ensuring the long-term sustainability and productivity of agriculture in a changing climate.